One way to answer the question on this slide about the relative basicity of benzene sulfonate versus this allylic anion is to use the conjugate acids and their corresponding pKa values. So go look up the pKa's of the conjugate acids and then apply the conjugate seesaw and the logic behind that to reason that, okay, if this is a stronger acid, this must be a weaker base, and if this is a weaker acid, this must be a stronger base. That is essentially a data-based quantitative argument for the relative basicity. We'd have to go look up this data. Organic chemists don't like looking up data. We like looking at molecular structures and making inferences about reactivity and relative stability from the structures alone. And we're going to start learning how to do that in this video with what I like to call the structural stability factors. 5 and really 4 super important and 1 kind of marginally important structural factors or aspects of molecular structure that we can compare between molecules when we're thinking about the relative stability or relative reactivity of two molecules to get a sense of that. And these factors are associated with measurable and consistent trends as we change the property or factor in a sort of a logical direction. So for example, resonance delocalization is one of these. As we introduce additional resonance delocalization of charge, this stabilizes molecules. So benzene sulfonate with 1, 2, 3 places where that negative charge is delocalized would be predicted to be more stable than the allylic anion where we only have 2 places where charge is delocalized. Additionally, the charge is on a less electronegative carbon, or carbons in the case of the allylic anion, and on more electronegative oxygens in the case of the sulfonate. This too would argue that benzene sulfonate is more stable and less basic than the allylic anion. So let's dig into these structural stability factors now, and these transcend acid-base chemistry. This is important to keep in mind. This is something that's very easy to forget when you get to more advanced reactions later in your studies of organic chemistry. Any reaction that generates benzene sulfonate can benefit from the stability of this anion. For example, we can start with a less stable anion on the reactant side, do any kind of chemistry, not necessarily proton transfer, any kind of organic reaction, and if that reaction generates benzene sulfonate, and that's more stable than the reactant anion, then that reaction is going to be favored, at least thermodynamically, in the forward direction. So we just noted that really better than memorizing or going and looking up and rooting through data, these pKa values, is developing the ability to see these structural stability factors, these aspects of molecular structure that lead to stability or instability, right, when they're missing. And keep in mind here that stability and reactivity are inversely related, and this has to do with the nature of energy on some level. A stable molecule is a low energy molecule. It's unreactive. It's happy where it's at. It doesn't want to become something else chemically. An unstable molecule is high energy and does want to become something that has a lower energy structure and so tends to be highly reactive. So stability and reactivity are inversely related. This is on some level deeply related to the idea of the conjugate seesaw as well. If an acid is stable, its conjugate base is generally quite reactive. If a base is stable, its conjugate acid is generally highly reactive. All right, so how do we know whether a molecule is stable or not? Well, there are five and only 5 structural stability factors in organic chemistry. These are basically the 5 reasons the 5 ways we rationalize things in polar organic or ionic organic reactions. And here they are in order of importance, from the biggest impact, the most important, the thing you should look at first, to the least important. The first is electronegativity and atomic size, particularly of atoms bearing charge. Next is resonance delocalization, which we've touched on already. Hybridization has an impact on the stability of electron pairs. Inductive effects, we'll talk about what those are here shortly. And then steric effects, primarily related to solvation, which we'll touch on at the end of this unit. And so notice that these form the acronym CRIS, dyslexic CRIS, as it was described to me back in the day. Charge, resonance, hybridization, induction, and steric or solvation effects. And most often we think about applying these factors in a comparative way, looking at 2 or more molecules and asking, okay, which of the 2 is more stable or more reactive? And it's incredibly useful and extremely important for this purpose. This is how we think about these stability comparisons rationally. And acidity and basicity is a big context in which we do this. One of the reasons we make comparisons so often is because stability is relative, right? If we're thinking about a reaction that converts some reactant into some product, we want to be able to think about the relative stabilities of the reactants and products. If we're thinking about two reactants or two reactive intermediates undergoing the same reaction type, their relative stabilities will tell us about differences in free energy and the thermodynamics of these two related reactions and all that kind of thing. Stability is relative because it's all about these deltas, delta G, delta H, delta S, that come into thinking about reactions and other molecular level processes. Generally, these stability factors are going to have the biggest impact and be the easiest to spot in charged species, in ions. The stability factors affect the energies of charged species most strongly. And so if we're thinking about comparing the acidity of two neutral acids, for example, or the basicity of two neutral bases, it's helpful to remove or add a proton, respectively, to think about the conjugate base or conjugate acid, which has charge. So to give you an example of this, let's compare the acidities of butane and propanol at the indicated hydrogens, here and here. The neutral molecules don't necessarily tell us a ton, right? Both molecules are neutral. It's hard to say, what the relative stabilities of the two neutral molecules are. But as soon as we remove a proton, some things start becoming apparent. So if we remove that red proton from butane, we end up with a species with negative charge on carbon that looks like this. If we remove that red proton from propanol, we end up with a structure that looks like this with negative charge on oxygen. Now, where is the negative charge more stable? Well, you may have a sense of this from introductory chemistry already. Pause the video and make a prediction here before we move ahead. On electronegativity grounds, we would argue that O- is going to be more stable than C- because oxygen is more electronegative than carbon. That makes the anion on the right, the conjugate base of propanol, more stable than the anion on the left. Now, what's the impact on acidity and basicity? Well, looking at the anions and thinking of those as bases, O- is going to be less basic than C-, right? Stability and reactivity are inversely correlated, and so O- being more stable will be less basic than C-. This makes the conjugate acid more acidic, and that's the conjugate seesaw in action, right? If a base is less basic, its conjugate acid is more acidic. So the real moral of the story here is, while the neutral molecules didn't tell us much, these anions had very clear structural features that our eyes were drawn to, and we could go right to one of the key stability factors. Here it turned out to be the electronegativity of the charge-bearing atom, and think rationally about how that difference affects the stabilities of these molecules.